My name is Jayaehandra Chilukamari. I am from Robert Gordon University, Aberdeen, Scotland. Today I am here to present my research work on a low complexity visual saliency model which is based on in-focus regions and center sensitivity. Before actually knowing what is a saliency model, let's know what is visual attention. Visual attention, whenever you look around, huge amount of information from the surroundings enters your human eye. The human visual system cannot actually process the whole of this information. So what it actually does is, in order to compensate for this inability, it actually picks the relevant information and inhibits the irrelevant information and start processing only the selected visual information. So this is called as selective visual attention. Now, a saliency model is a mathematical or computational model which is used to detect or predict this particular selectively attended locations by the human eye. So then what is the problem here? For the existing visual saliency models, there are two important characteristics. One is the prediction accuracy and another is the complexity. The state-of-the-art saliency models are extremely complex for them to be efficiently employed in many practical applications. So therefore, we propose a novel visual saliency model based on in-focus regions and center sensitivity. So the hypothesis is, whenever photographers take pictures, they tend to focus on the in-focus regions of an image. And we hypothesize that the in-focus areas have significantly large high-frequency information when compared to out-of-focus areas. So the other hypothesis is viewers are highly sensitive to the image center when compared to the periphery of the image. So in order to prove this, test this, what we have done is, we have actually converted an image to HSV color space and we have extracted the value component out of it. And this value component is actually divided into 8x8 blocks. And we have applied an integer cosine transform to these blocks in order to see the frequency coefficients. And you can see here, these two are the in focus. This is the in focus block and this is the out of focus block. You can see that the frequency coefficients enclosed within this region, and you can see that there are very high coefficients with high magnitude. Similar coefficients in the out of focus area have got a very less magnitude. This verifies the hypothesis that there are some coefficients in the in focus area that have got a very high magnitude. So then later on, but what we need is an automatic algorithm which can detect these in focus high frequencies which have got high magnitude. So what we have done is we have taken the 8x8 blocks of all the in focus area and we just made one 8x8 block corresponding to in focus area and one 8x8 block corresponding to out of focus area. Then we actually plotted the coefficients on a graph. So you can actually see that a very significant difference in magnitude occurs between the initial frequencies from 0 to 30. So what we have done is we have taken the peak frequencies where there is a significant difference in the magnitude and we just summed them up to plot a salient frequency map, and then we actually Gaussian smoothed it and contrast stretched to get a final focus map as shown here. Then, as said, the other hypothesis is that we are generating the center map as well. In order to get a center map, what we have done is we have taken a Gaussian anisotropic Gaussian distribution as shown with the standard deviations in the x and y direction as shown here. And these standard deviations are function of the resolution of the original image. And the factors that are contributing this particular center sensitivity is the photographer's bias, because photographers mainly tend to put the images in the center of the image. And the other is a viewing strategy where the viewers repeatedly orient toward the center of the image. So, and the other less influential factors are orbital reserve, that is a straight head position. The other is a motor bias, where the users tend to take short circuits when they are actually looking at the center. So the other one is the screen center and high level influences. So these two maps are actually combined according to this particular normalization. We actually normalize these two maps and then combined according to this equation. Then, as there are many parameters in this model, we actually use a hill climbing approach in order to get the best optimal parameters that gives a better prediction accuracy when we compute on a data set of 1003 images. And the fitness function is evaluated using a metric called as correlation metric. And the best parameters for this model are n equal to 12, k equal to 2, c equal to 0.95, and the alpha, which denotes the focus map, is equal to 0.35. We have compared the performance of the model with the state-of-the-art algorithms. You can see clearly that our algorithm achieves higher correlation when compared to the state-of-the-art in 2 out of the 3 metrics used. The other 2 metrics are normalized scan path saliency and area under curve. Now we have also compared in terms of computational complexity with the state of the art. You can see that the proposed model achieves a achieves a better computational complexity when compared to the state of the art. At the same time, it also achieves a higher accuracy. Now these are the 4 images from the data set. You can see that these are the eye tracking maps. People mostly gaze at the center of the image, and our model actually shows a higher intensity at the center and also detects the focus. And the future work, the conclusion is that our model performs better than the state of the art in terms of computational complexity and also prediction accuracy. The future model will take care of the temporal aspects of the videos. So I'm going to give you a live demonstration of my poster presentation. So you can see on the computer screen that a remote control is in focus, highly in focus. So mostly, I think it's very clear to you. You can see that there's a higher intensity shown on the remote in the right window. So now I'll just make it out of focus. See, now the remote is out of focus, and the right screen you can see that the intensity is very low on the remote in the right window. So this clearly shows that once I increase the focus, again it keeps detecting the remote. This shows that the algorithm is capable of detecting the in-focus regions, and this will be something very important for saliency detection. And another one, I'll show you a live video. You can see this video. Now this person is in focus. Again, after that, this person is in focus. So I'll just take it back, just to repeat. The focus keeps changing. Is in focus, then out of focus. So this is something which is happening even in the real Hollywood movies. So our algorithm is capable of detecting that. So and thank you. I thank ICC Berlin for giving me this opportunity to demonstrate my research work. I thank on behalf of my team and also on behalf of me. Thanks a lot.